Well, thank you for the introduction, Hendrik. Is everything visible on my screen? Is it shared? Audio coming through? Camera coming through?
Yep, everything. You can see your slide. I can hear you, and we can see you as well.
Okay, good. Then we can get started. So first off the bat, thanks to Neotys and Hendrik for organizing this awesome platform. It's obviously a very great way to learn stuff about performance engineering and share new ideas and discuss this with top experts. So I'm very happy to also be speaking here today. So a huge thank you for you guys. And I would like to introduce my topic. So it's performance testing on the unit level. And there's a bit of motivation behind this. And it's a couple months ago, I was working on a private project, some code, and it wasn't running properly, and it was slow, and I got a bit frustrated with it. So I called it potato code, and then I figured out that I thought it like it's couch potato code. It's not running properly. It's slow, and I don't know what's happening. So I decided to bust out a profiler and to check out where the time's being spent, how much. Where is everything being, what's the code doing, what are we doing? And I finally figured out where the performance problem lied, and I was like, okay, the problem was this dysfunction, fixed it, and the code was running beautiful. So I thought I had to jump through so many hoops just to get that running. How can I make this easier on myself? And how can I make this reproducible? Because I fixed it now, but what if I make a change that will make it worse or make it worse over time? I want to test that. So I was thinking, how can I get my code, stop my code from being a couch potato? So I thought, there might be a hole in the market for a cool open source project. So I busted out the Python and I started programming and I started building stuff. So I ended up building an open source project called Quick Potato. And that's also the logo on the right that you're going to be seeing on your screen right now. But because the team was Jurassic themed, I could not help myself into changing the logo into a potato dinosaur. So it's the potato dinosaur T-Rex. I couldn't help myself but to change it. So before we go into the meat of the presentation, I would also like to start off with a quote from Seneca, and it's a book from its book on the shortness of life. And Seneca says it's not that we have little time, but more that we waste a good deal of it. So what does a philosopher that's dead over 1,200 years have to do with IT? Well, we want to focus on the important bits in life. We want to focus on the hard problems. We don't want to backtrack and spend a lot of time with a lot of people fixing very small preventable issues. We want to prevent that. And good testing on the lower levels on the early stages of development in development life cycle is going to prevent us wasting our time. So that's also why I want to tell a bit of a story, and I want to tell the story about Hammond. Hammond is a great developer, a very smart one. And Hammond just packaged and built the last pieces of his code, and he's happy. And you can see it also in the picture. So he's already getting his glass ready to pour out some beer, and he's going to drink something. So now that Hammond pushes the code towards production, it's going to be tested. So the functional tests are going to be kicked off. Performance tests, security tests, the whole shebang is going to be executed and tested. That's awesome. So it comes through it with flying colors, and it ends up being in production, but there's something wrong. Something terribly wrong. Something has seeped into the production build. Something horrendous. It's a performance problem that has manifested itself in production. Oh dear. And now we have a problem. Now we have a performance problem running rampant on our system, and it's eating up our resources, it's eating up people, it's causing a lot of ruckus. We don't know which problem is causing which problem now. We think we have a major problem in the background, but we don't know what's happening. So we're going to call in the cavalry. The cavalry is if you spend long enough in IT, you're going to enter yourself up in a war room. So Hammond here is now in a war room, and he's waiting for everybody to arrive, and they're going to try and crack this issue. We're all smart people, so eventually we're going to crack this issue. We're going to find out what's the problem. We're going to use APM tooling, load testing. We're going to find it. And that's just a matter of time and a matter of how many people you're going to throw at the problem. But we are going to capture that data. We're going to capture the performance problem. So we can capture it, and we've prevented it. But how much time have we spent trying to figure out capture this small dino? I don't know, if there's 20 people in a war room and they spend an entire day there, that's almost a month of time spent that day. There's a whole lot of time wasted that could have been spent on more prominent issues. So how can we prevent this? How can we check every box, every block of code, every function or every class, whatever we ship? How can we test it individually and check out performance issues? How can we check out if that code is running in the way that we're expecting? So we don't want to get surprises when our users open up the box and there's a dinosaur in there ready to eat them. So we don't want that. So we want to test this earlier. So to give a good example and to really understand also how code can be impacted on that low level, we have to get into code. So we are going to dive a bit into code now, and we're going to see. But don't worry, I'm going to pull you through it. So what we have here is a piece of Python code. I'm going to walk you through what the code does. You don't have to understand it completely, so don't get scared if you're not familiar with programming. It's an example I'm going to do. So we have two functions, and the top one, generate large number, will generate a ridiculously large number. And to the left, you can see approximately what that number is going to be. That's super large. So then we also have on the down there, so the count length of number, the function below it, we have a function that will count numbers, and it will count how long that ridiculous number is. And it's going to come out that that's a very, very long number. So that's how this code a bit flows. So we have two functions that do two things, very basic, nothing too fancy. And counting numbers is something that a computer should be good at, because computers are good at counting and math. So we would really know for sure that it's very good at it. So one day Hammond writes this left piece of code, and Hammond is very happy, and he pushes it, it goes to production, and it works fine. And then a change needs to be made. So Grant makes a change to the code, and he changes int mat.log10 number to length string number. Grant also pushes this code to production, and everything works fine. Now the question is, right, both these two pieces of code have not been tested for performance. They haven't been profiled, they have just been committed. They both do the same thing functionally. So they output the same number, the same value. They do the same thing. They get the same job done. So no difference in there. But which one is faster? Because we haven't tested for this angle. So let's do that right now. Let's test this piece of code. So we see that Hammond's code comes back at 0.11 seconds. That's the fastest. Let's wait for Grant's code to return. See if it even wants to come back. And there it comes at 8.22 seconds. So we have a clear winner here. Hammond's code is faster. That's great for Hammond. But Grant made the less performant code, the worst in terms of performance. The difference between these is almost 7,000%. So it's a huge difference between them. So we want to prevent this. And this is one line of code that really makes this impact. And really also one line of code can have, if this one line of code could have this much of an impact, we could easily think like, oh, this could have been a database issue or some environment issue. We could easily mistake this for something more complicated than it really is. So this is obviously a weird example. This is if you're good at Python, you know what I'm actually doing here and what I'm abusing to get the response time to go that high up. But that's not really the point. It's mainly that one line of code, when it's badly designed, could really get a huge impact on performance. So to summarize what I just spoke about, we actually want to test a couple of things. We want to answer ourselves some questions, and we want to, and one of these questions is not to our liking, we want more information. So the first thing that we want to ask ourselves, did that code change impact the performance? The same way we ask, did my code change impact the functionality? We also want to ask, did that code change impact my performance? Also, what we would like to ask ourselves about our code is my code performing within my expected boundaries? Is it between 1 second or 0.11 seconds? Where is it in between? It has to be in between those boundaries. If it breaches one of those boundaries, we have a problem. It's either too fast or it's either too slow. So we want it to stick between those boundaries, and we can call that more of a sanity check, that it sticks between those boundaries. And if either of these two tests fail, we want to know which part of the code is actually the slowest. We could use profiling to do that. So, and we would like to have all these three things automated so it doesn't cost me much effort, that I can just include it into my unit testing and I can run it, maybe run the unit test a couple more times to get more samples. But I would want to have as many many samples as I have, and I want to answer those questions, those 3 important questions. So to do that, I'm going to jump into a demonstration and actually show you. So I'm going to quit my PowerPoint real quick, and I'm going to swap over to my IDE. Let's see here. So this is also, to the left, we see the same code that I shown in the presentation. So it's the same code, the examples are the same, but there is one key difference. This code has been equipped with Quick Potato. And Quick Potato has something which I call intrusive profiling. And intrusive profiling means that we're going to smack a decorator on top of it. So if you're familiar with Python, you're going to know what the term decorator is. If you're not, I'm going to quickly explain it. A decorator is basically a function within a function, meaning that if one of these pieces of code, which I'm going to highlight right now, is going to be executed, then first this function will be called. And everything that is in between those 2 functions will then be called. So when this one's called, it's going to watch this function run. And the same goes for the other one. So they're basically, you can consider them watchers. They look at each other. And these decorators are intrusive because we actually put them on top of our code and we check out, okay, how fast is this running? And we also type it in the code. So if we have an existing code base and we wanted to add Quick Potato into it, then we would have to add those decorators to every function that you would like to test. So they have a technical purpose because Quick Potato uses them to test their code intrusively, but they also serve a human purpose. And that human purpose is to signal to developers, hey, wait, this method that you're going to touch is actually very performance critical. This is a method that might be executed 10,000 times. And it has to be really fast. If you change something, then it might not be working in the way that we want to anymore. So they act like a sort of warning flag. So obviously, I'm also working on ways to do this non-intrusively, which is totally possible, but I haven't gotten time to do that yet. But I really like the idea of flagging them and then also showing to other team members, hey, wait, this is a performance critical function. And it's just like a watch out sign. So to the right, I have my first piece of the demonstration. I'm going to highlight it blue, so it's really quickly showable. And to the right, we have a piece of code that's the same to the left. You can see the same code, same decorators, but this time I'm executing, and I'm highlighting it blue again. And we have large number, count length of number, right? And we're going to run this code. And because the performance critical functions have been attached to them, and Quick Potato has been turned on in the config file, it will actually start collecting information when these 2 functions are executed. So let's do this. I'm going to execute this code really quickly. I'll wait a couple seconds, profiling to happen. And there it goes. And if I would hop over to a database server, so I have MySQL installed and Quick Potato connected to a database server. It's not mandatory to have a database server. It's just easier to show you if I have a database server. But it's also running SQLite in the background if you don't want to use MySQL or Oracle or whatever you prefer as a database server. So let's quickly go to the Quick Potato default database. If it doesn't have a test case, which I'm going to go into later, it will spawn a default database. And in that default database, it will start saving information. So quickly, I'm going to show you how this information is structured and how it all works. So if we go to the time spent statistics, we actually can see which functions. It might be a bit small, so bear with me. I can't really change that font. But we can see, for example, here on the name of method under test that we can actually see which method is being tested and which sub-functions are being called by that method and how long they take and in how much volume they're being executed. And I have a great slide to show you later how that shows on a bit more complicated code because this is really simple code and it's not going to do much. So because we have a wealth of information that we collect during the execution by just attaching the profiler to it. And for the people who know Python, I'm using C profiler to actually capture all this information and just spin it back to a database. Not in my opinion, the best profiler. It could be better because you also have line profiler for Python that does it way more in detail, but it gets the job done and it works just fine. So with this information, you could make flame graphs and all kinds of cool stuff. But besides that, I also am saving system resource statistics. So I turned this on. So when this thing is running, it also is going to sample my CPU. So it's going to check out, okay, how much CPU am I using? How much memory am I using? just to be able to see, create a graph afterwards to see, okay, my code, which I know is going to be CPU intensive, is using this much CPU in the process, and this much system CPU is being used. It's the same for memory. So still working that out a bit, but it's in its bare bones right now, but it's working quite fine. So that's all very cool. So I'm going to switch back over to my IDE, and we're going to actually switch over to the second type of test. So we're actually now going to actually test the performance of my code. And we're going to do this with what I call a UPT, also known as a unit performance test. And you can do this real quick. So I'm going to go from top to bottom in the code. So we import in Python, we import all the stuff that we need. So if you know Python, you're going to see like, oh yeah, that makes perfectly sense. But if you don't, we're just going to import all the stuff that we need to run Quick Potatoes unit test framework. Then we're going to define a test case, which is very important. So we have to give it a name. We have to give the beast a name. And we're going to call it UPT boundary. And then we're going to set a max and a min boundary, highlighting in blue right now. And we're going to say, okay, we're going to set a max and min boundary for the average. And it's going to be maximum 1 second, minimum 0.001 second. So that's our boundaries. Between those two boundaries, we expect our code to behave. If it doesn't, fail the test. And then I can look into the profiled results and see, oh, this happened. And then I can make tweaks accordingly. So obviously, I need samples. So if I run, it's possible to run this once, but then you have only one check on one function. So if there's a little bit of fluctuation, you want to kick it off a couple times just to see if it always comes back at the same speed. You can do it 100 times, 10 times, 20 times. It depends a bit on how you want. The sweet spot that I saw for most of the code that I used to test it under is around 10. And for more complicated ones that have fluctuation, I use 100. And this is obviously going to take some time to run. So the idea is also that this runs in the background. I'll come back to this, to the accuracy a bit later in this talk. So we run this code, we get the information out of it, then we're going to verify, benchmark against the set boundaries, and we're going to get a Boolean back to true or false, yes or no. And then we're just going to say, if result is true, then we're going to print pass, or else we're going to print failed. So pretty easy code. So we're going to run this, and we're going to get a result back that's going to say passed. Let's wait until the interpreter spins up and executes my code. And there it goes, passed. Awesome. So we can actually see now that we were successfully to check if it sticks between two boundaries. Is my code operating between those two boundaries? If not, then we actually want to fail it. So switching over, so boundary testing is cool. Maybe if you, as a team, agree on certain thresholds that you're going to set in your code and say like a database call cannot take longer than 3 seconds, or this type of calculation cannot take longer than this amount of seconds. So if you define that, you kind of stick to it. And if weird things starts to happen in your code, then the tests are going to show that. But the most powerful test, which I find, is the regression test. Because we want to, basically, most of the time we're working on code that already exists. And it might be running under maybe 12 seconds on an average of 12 seconds. So we want to know if that changed. So did I go from 12 seconds to 20 seconds, or did I stay within that 12-second range? To do this, we want to do a regression test. And it works the same as a boundary test. As you can see, it's the same structure, different name, same amount of sample size. Only thing is different is going to be this: verify benchmark against previous baseline. So it's going to take a baseline that we've done before, and it's going to test it against a benchmark. And that's cool because it will then tell me, okay, your code, the change that you just made is different to the change that you just made. So it can actually tell me, oh no, you made a mistake, it's slower. Or you made a mistake, it's faster. Or no, it's slower. So if you get a warning, for example, it's faster, then we know, oh, because it's faster, I now know that I've made a performance improvement. But I also want to be triggered if I do this, because it could be an adverse effect or a problem that I don't want. Maybe I don't want it to be faster. So I want to be triggered if it isn't the same as the previous time, because I want a human to look at it once that happened. So same with the code. It's going to say passed or failed if it's done. So let's run this. Wait a couple seconds. The interpreter again to spin up and go back to results, and there it goes. It says passed again. So that's cool. And I've run this test a couple of times to make sure that I had a baseline. So it actually says now passed, but this is still not really what I want. I want this to be integrated in a unit test string. So that brings us to the last Python script that I have written. And it's going to be. So we do the same thing again. We import all the bits that Quick Potato needs and the code that's under test. And we import a unit test. That's a Python framework for unit testing. So we create whatever unit test we need. So we create a class here. We attach unit test, and you get these, if you use PyCharm, these cool arrows that you can click on, and then it will execute the test. Same stuff again, define a test case name. Again, do a sample, and then we do the same thing again, verify, get that Boolean out of there. And then we are going to say assert true, and if assert true is the result is true, then it's going to pass a test. If not, it's going to fail it. And we get this cool red text in the editor. So let's run this. Run unit tests. Okay, wait a second. Okay, it's running here right in the background. And it says test pass, 1 of 1, worked fine. So we want to see this fail. So we want to be able to see that it captures the failure. So what we're going to do is we're going to change the code. So we're going to take this and we're going to implement the same error that we actually created in the previous test in the PowerPoint. So we're going to change this int mat.log10, which is incredibly fast, and we're going to change it to something slower. So we're going to say link string number. And by changing this to by changing it like this, we're going to introduce a performance problem. So this runs around 8 seconds. So if I execute this, it's going to take some time. So let's run. So it's going to come back eventually with a pass or with a fail. So in the meantime, while this is running, I'm going to switch over to Tableau. So if you're unfamiliar with Tableau or you're just joining and you didn't see Stijn Schepels' presentation about Tableau, I highly recommend to watch that back because it's an awesome presentation about how to use raw data and how to work with that. Let's switch over to Tableau real quick, and I'm going to show you how this would look under more under more complicated code. So here we have a database query running through SQL Alchemy, and I have played around with it a bit. So I executed this an X number of times, and one time I decided to throw a time sleep in there just to make sure that it failed. Pretty diabolical, just to put a time sleep in there. So I threw a time sleep in there knowing that this would fail, obviously. But cool thing about this report, let's make this a bit bigger, that we can actually see, for example, that this is green, 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 failed. And also when we look here at the raw data, that we can actually see that we have a lot of these weird little dots here with which are all time sleeps, as you can see, because they all go up and they're all around 0.5 seconds because I made them variable. And it fails the test automatically because this block is red. And once I then change it back and remove the time sleep from the code, it goes back down and it starts working again properly. And then we get a pass every time. So you see this very colorful, bubbly graph at the bottom. And that colorful, bubbly graph is actually the profile results of which Quick Potato capture with C profile. Every single little ball in there, the bigger it is, the more volume that transaction had. So let me quickly highlight one, pick a cool one, find one that I wanted to see. So when I select, for example, here, write bytes or here, the time sleep here, we can actually see, okay, it's highlighted. We can see this one was executed around 1 time, and you can see it perfectly when it's happening. Let me find a bigger one. There it goes. So here we have, for example, this method here, how's it called? Method receive into socket object. So socket object. You can see this has been executed more times. The balls are bigger, and there are more balls of them on the time axis. We can actually see, okay, how much. Where is my time spent in the code? It's a bit like a flame graph, and I really like the flame graphs, for example, a lot that they use at Netflix. And I really like that because it also mimics the same idea. So with Tableau, I tried to recreate the same kind of thing because I don't have a GUI yet for Quick Potato where I can actually just show this off in a web browser or in some sort of manual thinker GUI, and I don't have that yet. So now I'm using Tableau to visualize this, but this is something that I would really like to have in Quick Potato as a GUI. So this works perfectly, and I can actually see a lot. Let's switch back real quick to my my IDE, and we can see here that we have a failure. So this ran for about 1 minute and 17 seconds, because high response times. So this is now saying, okay, false is not true. Yeah, that's correct, because this thing is going to output false because we have a change. So if I would hit Control Z and would change this back to what it originally was, rerun the test, and wait a couple seconds, it's going to say pause, because now I actually fixed the test, I removed the bug, and it's going to say, hey, good, everything is fine. Your code's good again. You can continue. So how am I doing this? How am I making sure that this happens? So I'm using a statistical test called the t-test. And in my dashboard right here at the bottom right, you can see a visual representation of it. So if you're unfamiliar with statistics, I don't want to get all too deep into it because it's a bit of a difficult thing to explain. But if you look to the right, the bottom graph, you see those orange bars. So that's the t-value. And then we see the blue bar, which is a critical t-value. As long as that t-value is below that blue bar, your test will pass, because then it's in the degrees that you want it to be. Not too much regression. The data sets look like each other. But once it oversteps that boundary, it's no longer the same data set. There's a discrepancy in between them, and we want to fail it then. So that's how this works. That's the t-test underlying making those decisions. So I've tested this again on my computer, turned it on, used the same code, no regression. So the same code, and ran this for 10,000 tests, 10,000 times, and then 100 iterations. And I actually got very little failures because of the system. I think it was around 5%, and that was on a very low spec system. And once I tried this on my higher spec 12-core machine, which I use for gaming, it worked perfectly. I didn't get any issues on that. So to quickly go back to my PowerPoint, slide, I would recap the dashboard real quick and really show this one more time. That this is in my opinion, a very powerful view. And Quick Potato is an open source project. I would really want to have this into a GUI, maybe more of those flame graphs to really represent how the code is being structured. I tried to get it in there, but I struggled a bit to get it working in the way that I wanted it to. So that's why I'm using Tableau right now. But that's about it. So before I want to close, I want to ask if anybody is interested in collaborating on this project. If somebody's like, oh yeah, this looks really cool. I want to help. I want to build this cool. I want to help bring this to the next level. Hit me up on LinkedIn. Let's discuss. Let's see how we can help each other, and let's see how we can do it, or just pull it from the GitHub repository that I've linked here. Just pull and play with it yourself. If you want to use it, be my guest. It's open sourced, and it's on GitHub, and have a play with it. So that's about my presentation. I would like to know if anybody has any other questions or discussions or feedback. That's about it. I want to thank you for your attention and your time.
All right, thank you, Joey. So let me enable the webcams of the various speakers that are currently connected. So I see Luca is there, so you can enable. Andy is still connected. Roman Leandro is he's getting Dutch. He's completely orange. And Alan as well is connected. All right. Cool. All right. First of all, thanks. I really like that framework. One question that I had, it said that you have to enable the framework through a config file. And the big question that I have is, from the moment it's enabled, would that profiling be executed for every code execution, or will be only limited to the test case that you have built in your unit test?
No. Once it actually is enabled, it will, like a sort of poor man's APM solution, it will start collecting information. So it's possible if you don't disable it, it will start running on normal operation and will start collecting information and profiling your functions and your system resources. So once you deploy this to production, you have to disable it. So it's all programmable. You can just say options dot and then the option and then disable it, and then it saves back to the config file. Or you could do it manually, open the config file, type it, and set to false. You can also do it through Python programmatically, which is cool because then you can play around with it and actually turn it off and on the fly. All of the settings are like that. You can also just on the fly decide to save to a database server or go back to SQLite. So that's all programmatically, all on the fly. Nothing too fancy.
And the second question I had is, so you're collecting everything on currently it was SQL Server. Do you have, for example, it says, okay, so you have consumed that amount of resources, and does it provide a line of the code that has consumed, that has codes that consume?
Yeah, the profiler does that. So the C profiler gives you the exact line, approximate line of the code that actually is showing the issues. Not super accurate. There are better profilers out there. Like I like Python's line profiler. Then you actually get a line-by-line overview, but it didn't get it to work in the way that I wanted to, because I want to be able to spin this profiler up on the fly. I don't want to profile the script at the end. So really, it's just Python, and then your script name, and then add the profiler to it, and then I get a result back. I don't want that. I want to be able to program it and do it on the fly, because then I can add it to my unit tests. I had a lot of difficulty doing that with more nicer profiling tools, so I decided to use C profile. Maybe thinking of building my own profiler, but that's really complicated.
And the other question I have is, do you think that would be possible in the dashboard that you showed us in Tableau, for example? So clearly you have a test that has failed, so everything is red. You can see from a dashboard you've built that obviously there's a problem. Do you think that you can attach, for example, the origin of the problem as well? So then once you see that there's a failure, that suddenly you go through the different metrics that you've collected through the profiler and say, okay, so your regression is basically is come from that line or that part of the code.
Yeah, the thing is, the profiler itself, right? It says that. So if you would add those points, I didn't thought about doing that, but this gives me another angle. We'll talk about that in a second. But with the, if you can just drag and drop the file path and the line number to Tableau. So when you then hover over the test results, and you see, oh, okay, it was this file and this line number that was the slowest. You can actually do that calculation in Tableau. I would love to get this into as a web application with a GUI where you can just do this all with a mouse click, but you can do it in Tableau right now or calculate it with a SQL query.
Cool. That's pretty cool. So that was my own questions. I see Andy is looking with his detective eye. So Andy, do you have any question? Because it seems that it brings your attention.
Yeah, I have a question. So from first, the annotations, I'm not sure what they're called in Pythons, but the annotations that you put on the method, so they are basically just there so you know what is your root level method. Because once you turn on the profiler, you get a lot of profiling information. And so these annotations are really just for you to say, I'm alerting in case there's an abnormal response time to that method, correct?
Yeah, it does. Yeah, sort of. Once that it's called a decorator in Python. Once they're attached to that method, it's the root level. So it starts only measuring from that point, and once it exits that function, it will stop measuring. So it will only measure between those points. So the decorator is the start, and once the function finishes, it goes back to the decorator, and then it disables again. So that gives you the ability to filter out functions that you don't want to profile or that are not necessary to profile, or maybe too complicated to profile.
But that also means this is what you use to control your C profiler. So is the C profiler, you can actually turn it on and off on a thread level, or how does this work? Yeah.
On the thread level. So once this is executed, because the decorator will be executed first, it will
you turn it on. Okay, I get it.
lift on the track to measure everything. That's quite cool.
Yeah, and I mean, what would be great in the output? I guess right now, I think it just says failed because of a performance regression. Do you also show why it failed and how much it deviated? And because I didn't see that, because that would be interesting, right? Do you fail by 1%? Do you fail by 50%? Do you fail by how much?
Not yet, but I do calculate that. It's not yet included. I do those calculations, and I have them all available, but I haven't added them yet. So I was thinking, indeed, what you were saying, just dump metrics once it fails and say like this is how much it changed. I am working on that, but as of now, it's not in there because I haven't had any more time to work on it.
Yeah, and do you have, so every time you run a test, do you give that test an ID or something that you can then uniquely identify the run? Yeah.
Yes. Every test, once it runs, it gets a unique test ID. On top of that, also every function call gets us a unique user ID. So then you have a UID per profiled function call, and you have a test ID per executed complete test.
Cool. Well, if you have all that enough, and you need some UI, some web UI, you could build a Captain SLI provider, and then use the Captain Bridge, at least for the high level. You know, I could see every method that you were annotating or decorating as a critical method would become its own SLI. And then you would at least get a nice heat map and say, hey, over the last 20 builds, here is how my heat map looks like. And you can always see if a problem happens, it always happens in these methods, because this is the great thing about the heat map, because you always see patterns in which part of the code actually things get slower or faster. This is a visualization that also Stain, I think, used in his last PEG presentation, which I really liked, his heat map visualization, where you can see then, okay, here's actually a hotspot of a couple of methods in the same package that all of a sudden, if something gets slower, they all get slower. And I thought that was pretty cool.
Yeah, I have the same idea, but it's just not done yet. I'm working on it still. But I also thinking of creating a heat map, because I really like those flame graphs to add those. Mm-hmm. That's the Tableau dashboard looks like a bit of a discount flame graph.
Mm-hmm. But you can do that. Stay tuned at 1 a.m. There's a open source product built by Netflix, the Flame Commander, so you can maybe utilize the work.
Yeah, definitely tuning off for that one.
And a question. So I thought that so it means that the developer says, "Oh, this is critical. I'm gonna enable decorate this function, and this is critical. I'm gonna decorate that functions." And I was just thinking while Andy was speaking. So if I was able to get how my code behaves in production, scanning something and say, "Oh, this method is pretty slow in production," so I'm gonna go back to the code, add the annotation there automatically through a batch or something. So then for the next unit test, I will have all the decorator in place on the methods that we observed that we know that are slow, because we observed that they are slow in production. So that could be also something that would be cool. Auto decoration.
Yeah, exactly.
Cool. Great. Roman, do you have any questions for Joey?
Yeah, sure. Questions and remarks. So thanks for the talk. It's really nice to see something done in Python. I also liked a lot the statistics part. I think this is something I'm gonna think about later a lot. Also using the t-test here is a really cool approach of testing your own results, because you want to baseline, right? So if it comes to pipeline and narrowing down the entire data set of raw data to individual values, I think this is really something we should look into. I have a question also. How did you actually trigger generating the test data? I didn't get that part. I saw the individual executions, and for your analysis and all the data points that you showed us, the beautiful ones, how did you get these? How did you kick it off?
So the decorator, which I showed in the beginning of the demo, those yellow lines of code that says add performance, it's critical. They carry a function for C profile. And a decorator in Python is kicked off first, and it exits in a decorator. So because that C profiler then encapsulates the function that's underneath it, and as soon as it's encapsulated, it will watch that function and capture everything it does. If it makes a other function call to a third-party library, it will capture that and see how long it takes and how many times that it does it. And that information is then from the decorator stored in memory and then rapidly shot to a database. So it uses synchronized calls to rapidly shoot small packages to the database and to upload it all into the into a SQLite or MySQL or a Postgres database, whatever you fancy.
Well, thanks. I even got that part, but the details here to know are quite nice as well. I was thinking about, because you have this is for one method, one flow, but you had hundreds of iterations. So did you just use a pipeline, or how did you generate the automation, or just a loop over your unit tests?
Just a for loop. So I just executed
all right, yeah.
Times or 10,000 times.
Wouldn't it be a cool thing, just brainstorming there, to have something that's triggered on a commit or something like that, just to have some sort of automatic evaluation?
Oh yeah, for sure. So the idea is that this is meant for developers, but this can easily be integrated into a CI/CD pipeline. Because if you kick off your unit tests through a CI/CD pipeline, you can also kick off your unit performance tests through a CI/CD pipeline, and then measure it also. And then
that's what I thought, yeah.
And the output of what comes out of Quick Potato, you can then use that to further analyze, or just base yourself on Quick Potato's analytic abilities, pause or fail the pipeline, to just stop it right at the unit test level. And because we're testing earlier, and also because we are adding those decorators, we also hope that developers think more about the design of their code and consult performance engineers or performance testers more earlier in the development life cycles to talk about design choices. How are we going to do this? Does this need to be tested? That kind of stuff. So Quick Potato also hopes to get a culture shift towards performance and not just tunnel vision towards functionality.
Mm-hmm. Good. Well, I think if you go this way, yeah. Sorry, Andy, I'm just linking to you actually. I think if you go this way, Captain would actually be a really good choice. Yeah.
And one more clarifying question. So the decorator's responsibility is collecting the data, and then at the end you had your result variable where you actually call some method. And this method, one is called baseline, one is called something else. This actually contains the logic of then pulling the data from the database, the historical data, and then comparing it, correct?
Yeah, so that contains the logic. So that's once the code is being profiled, it will create an object called a UPT. That object is shared among all the entire namespace, put it like this. And once you access that UPT object, then it will actually start. So once you access it and set a test case name, it will then trigger all the logic to set up the entire testing infrastructure. If it's not, then it's just a prepared model, a prepared object to start testing your code. So that's how it works. It's the best way to if you really are interested, I could walk you through the code offline, show you that. But it's really cool.
Yeah. Now, if you could, I know you have it in the slides, but can you maybe post a link to your Git repo in the chat window?
I'm ready. So wait, let me go to the chat window.
I see that Stain is connected. Before I ask a question to Stain, I'm gonna ask Luca. Do you have any questions related to Joey's presentation?
Really love this presentation. It's nice to see some Python. And I wanted to ask if there is any functionality to, let's say, kind of reference or bookmark any specific test in order to have compare those results to, say, the production environment in order to make it fail if we have performance that are worse than, say, production environment or just fixed values.
That's I don't really understand your question. Your question, how I interpreted this, is you want to compare the information that are collected during profiling statistics from production?
Yes. Yes, and compare it for, say, the commits from the production environment in order to let the CI pipeline to fail if we find any test that is worse than what we will get with the current deployment.
Yeah, Quick Potato, you can force Quick Potato to compare a different test. So if you Quick Potato will just always take the latest test, so the previous one. But with some logic that you can write on your own, because you want to make those decisions yourself, you can force Quick Potato to take the previous test that you want. For example, you can use a static test, so you run one iteration through production, and then you use that as your baseline to compare the new test for. You can see how much difference is there between production and what you just did. You can do that too, but it just depends on how you're going to execute it in which order. So how I did it is basically just development.
Okay, thank you.
Alan, do you have any questions for Joey?
Hi, not especially. I'm a fan of the Quick Potato. It makes me wish I was working with Python. Unfortunately, I'm not, but I guess a dumb question is if we were wanting to do a similar thing, but for, say, JavaScript, are there principles of what you've done that we could reuse, or would it be start from scratch?
So everything in Quick Potato is built for the Python programming language, so nothing is reusable for Java
or JavaScript.
But the entire concept, I think it's possible in any modern programming. It would also be possible in Java. I'm not an expert in Java, but I strongly believe that it could be possible to also recreate the same thing for Java.
So it's going to be
a bit more difficult with the JVM languages because it's not as simple to do this kind of unit level benchmarking in that the JVM kind of fights against you by optimizing things and so on. But yeah, there are some techniques around it. But yeah, it's great what you've done for Python for sure.
Yeah, the Python makes it a lot easier, for sure.
But basically, you can definitely do a call for action for the attendee. Says, "Hey, I need an expert in JavaScript. I need an expert and then we can do different flavors of potatoes. So potatoes with cheddars, potatoes with blue cheese. We can be very creative. I'm pretty sure about that.
The idea is also
what about open telemetry? Wouldn't that be a great way? Right, open telemetry is an open standard, and you have libraries for pretty much every language out there. And then you would all agree on a standard on instrumenting code, and then it can then be used for your type of work on the unit test level or in the development, and it can then also be used for production monitoring.
Yeah, I agree. That would actually be great, but I don't know. I really don't know if that's how that could be achieved, to be honest.
Well, it's similar what you're doing with the with your decorators. I mean, check out Open Telemetry. It's an open. I'll send the link in. And there's also actually when Ellen asked for JavaScript, right? So here's the JavaScript implementation in the chat window for Open Telemetry, which means you're just as you do ask developers to annotate their code or to instrument their code manually, but then you get a standardized trace data that can then be consumed by monitoring tools. It can be used by your tools.
Sounds really interesting. I'm going to look into that.
So I'm looking at the time. Last questions for Steen. I think you're muted. Yeah, we don't hear you. Oh, no. Okay. I don't know. Maybe you have a problem with your audio settings in Blue Jeans. But yeah, no. All right, we can figure out. But otherwise, we can still drop the questions in the chat, and we can maybe try to answer it on the next Q&A session. So it's time for a break. I would like to a big applause for Joey. Thanks for your presentation. I really like, by the way, all the design work that you made with Dr. Hammond. So that made my day.
Yeah.
I really like
it. I made this with a friend, so shout out to Kevin Tonk for helping me with the images. He's really great at Photoshop.
Yeah, it seems so. Pretty talented. I probably need him for the next commercial video or fake commercials again, because I think he seems a lot about that.
I should definitely hit him up. He's quite talented at all that stuff.